One thing I want to just mention that since your regular semester classes are in have already started in full force, and also my regular classes are also going on in full fledged, so it will be now very difficult for find a mutual time. Okay, so what I have decided, if you permit, if you allow me, I will try to very quickly complete the single pair shortest path problem like distrust algorithm, and then I will also touch upon the counting sort and reading sort today. Okay, because next week I may not be able to take any extra classes. I have enough pressure. Maybe if we find our mutual time in the next week, we may cover hashing and try and suffix tree. Uh, so I'll try to complete the remaining portion of the graph, as well as the counting sort and reading sort are very easy to understand. So I'll try to complete it today. Will it be possible for you to attend this thing? It may take more than 1 hour, a little bit. I will try to move as fast as possible.
Okay, sir.
Okay. Because see, since your regular classes, both of us, I mean yours and mine, is going on in full fledged, it will be very difficult for find a mutual time from next week. And next week I really am terribly busy, and may I have I mean plan to complete hashing also, and if possible try and suffix tree. Those are very advanced data structures which I usually teach uh, extra in every DS courses. But let's see. Today, let us try. So, without wasting much time, let me start my presentation. Is the presentation visible?
Yes, sir.
Okay. Okay. So, how many of you have tried to solve the MST problem with the graph I had given as an exercise? Did you solve that? Anyone? Oh. So your silence says that no. Anyway, so let us discuss shortest path problem, because this is also very important problem. I mean, in many real life applications, you will be finding uh, this problem. Uh, I mean, very popular. Okay, so the problem looks like this: a directed weighted graph with some weight function. I mean, this weight function will determine the edge weights, and there will be two dedicated vertices. One will be termed as source, and another will be sink or destination. Now we need to find a path from S to T whose weight is minimum. This is basically the most simple kind of shortest path problem. This is called single source and single destination. Okay. So given this undirected graph, actually shortest path problem you can also apply on undirected graph also. But the algorithms consider that graph is directed, and almost all popular algorithms which defines shortest path problem and solves the shortest path problem on directed graph can also be directly applied to solve it for undirected graph also. So for this example graph, the path shown in red is the shortest path from this designated vertex source S to T. Okay. Now, how do we find? Before that, let us consider the different variants. As I have mentioned, the most simple one, the single pair shortest path problem. That means there will be dedicated source and dedicated destination. And this is just the special case of, we'll see, a single source all destination vertices. I mean, most of the popular shortest path algorithm, including Dijestra's algorithm, which we will discuss here, they they actually able to find single source all destination shortest path. That means from a source, the it will be able to find the shortest path from the source to all other vertices of the graph. Okay, and when this is solved, that means you can easily solve that single source, single destination when the source is fixed. Okay, for a typical source, if you solve this single source shortest path problem, that means from that particular source, you can you can have any destination, the shortest path is available to you. There is another very important variant which is called all pair shortest path, uh, which we will not discuss here. Those who are interested, they can refer to any standard book or literature. There is a famous algorithm by Floyd and Watzel to solve this all pair shortest path problem. Okay. Now, why this single source shortest path solution works for single pair shortest path also? The basic property is that when we have a shortest path from a source to a destination, it actually hops through several vertices. Okay. Now, if your shortest path solution is able to find a shortest path which visits all the vertices of the graph, that means by default, you have been able to find the shortest path to from source S to any Vi, which appears in this shortest path from S to T. You can easily prove this claim or property just by just the method of contradiction. Now, why? Because if you see, if this, suppose this without loss of generality, some intermediate vertex Vi you consider. Now, if this S comma V0 to V1 up to Vi, this is not a shortest path from S to Vi, that means there might be a shortest path from S to Vi which could replace this subset of this entire path and which could have been the actual shortest path from S to T. Are you getting my point? How this property can be proved by contradiction? So any vertex which appears in the shortest path from S to T, for that vertex, shortest path from S to that vertex is already within this solution. Because if there is some other solution, then this cannot be a shortest path from S to T. Am I clear?
Yes, sir.
Okay. So that's why this property actually helps us. We will see also whenever we are using Dijestra's algorithm to find a shortest path from S to any T, since Dijkstra, philosophically performs a BFS and covers all the nodes to find out the shortest path from S to T in the forward pass, you can easily write appropriate traceback code to get shortest path from any vertex from this designated source. Okay, let me explain that. So basically, the philosophy of Dijkstra's algorithm is like this. It works on both directed and undirected graphs. Okay, so input is weighted graph and source vertex such that all edge weights are non-negative. So the destination vertex may not be specified. Okay, because it will automatically be able to find the shortest path from all other vertices from the designated source. But for a specific problem, for a specific application, you may just want to find the shortest path from S to AT. In that case, you can just refer that T, and you can leave the other shortest path which you are not interested in. But one pass of the forward pass of Dijestra's algorithm will be able to take you through uh, in a position where you will be able to find shortest path from S to any other vertices. Okay. So output will be length of the shortest path or the shortest path. So this depends. I mean, we'll see in order to find the shortest path, you need to add some traceback code properly. So this parent information, as we have already seen in case of solving Prim's, I mean MST using Prim's algorithm, we had additionally kept a bookkeeping to keep the parent relationship so that we can form the tree properly. Similarly, the naive portion of the code, uh, which I mean, naive implementation of Dijestra's algorithm may not give you the path. It just calculates the length of the shortest path. But additionally, if you keep that type of bookkeeping to add the parent information for every possible step, then using that parent information with a traceback code, you will be able to find the actual path. Okay. So basic idea is very similar to the Prim's algorithm. Okay, it maintains a set of S of solved vertices, and at each step, just like in MST also, we have we will start with the root. Here we will start from the designated source. Okay, and at every step we will be adding the closest vertex. Closest means having the least distant vertex within these solved vertices, just like in MST we also do. But the, I mean, the computation of this closest vertex will slightly vary depending on, since it is not a MST formation, it is shortest path formation. We'll see. Just the definition of this closest will be slightly different from the Prim's algorithm. Otherwise, the entire philosophy is almost similar to Prim's algorithm. We can easily see. Okay, so as usual, it is also a greedy algorithm and it is similar to Prim's algorithm. And it also, philosophically, as I mentioned, it performs a breadth first search. So it explores all the nodes using a breadth first search. Okay, and typically, if you consider a graph, if an undirected, I mean, if weights of the graphs are one, that means the Dijestra's algorithm will turn out to be a BFS, nothing else. You can easily see when I illustrate that. Okay, so this is the formal algorithm. You can just see that it is almost similar to Prim's algorithm. Here, see this traceback code I have not written, this parent information. Okay, but you refer to that Prim's algorithm from which you can easily, while updating this, you have to update the parent. Okay, and you can easily see this clause. The if clause is slightly different from the MST algorithm. Here, what we have done, weight less than DW, we will update with this. But here, if distance of V, that means that the D value of V here, it is greater than D value of U plus the current age we are considering, then we will update the D value of V with not only the D value of this, I mean weight of that, we'll add that this value of U with that. I mean this is the extra part we are doing. Okay, here what we are doing in MST, if weight less than DW, then we are updating DW with straightforward. We are replacing the existing DW with the weight. But here what we are doing, here is something different. If our this weight of DW basically added with the distance of DW is less than dist V, then we are updating dist V with dist U plus, because this is the path we are trying to calculate, shortest path. We have to calculate shortest path from that particular source. Okay, so that's why we are adding the cost of, already this you actually referred the shortest path length from S to U. So now I have to, this V should represent the shortest path length from S to V. So it will obviously, it will add the current edge weight with the existing path weight up to U. That's why this change. Are you getting my point?
Yes, sir.
Okay. So it will be more apparent when I'll illustrate with this example. Okay. So important thing is that I need to maintain this priority queue, this S of solved vertices. So initially it will be empty. Okay. And this dist values. Okay. This extract mean is nothing but getting the head from the queue, because this name is something different I have used here, but basically it is a priority queue. This function will extract the head of the priority queue depending on these distance values. The minimum distance vertex will be included as U. Okay. So starting point, the source S, it is given. Unlike Prim's MST, here it is already given. So the d value for this will be 0 and all remaining d values will be infinity to start with. And the set of solved vertices will be empty first, and priority queue will be like this. Only at head S will be there, and all other nodes are having same d values, so they will be in any order. No problem. Okay. Now, as I have said, when you have already considered S, that means now you are ready to see. Initially, the entire graph was unavailable, invisible to you. You had only idea of the source. Now, when you pick up the source in this S, then all the directly adjacent nodes will be visible to you, and accordingly you will update their d values, as well as you will update the settings of the priority queue. So next step will be like this. So extract mean will extract S. Obviously, it will be the obvious steps, first step. So S will be removed from this PQ and will be put into S. And you see, all the distance values will now be updated using that particular clause. This all for all neighbors of u is now S, and this will, using this relation, everything will get updated. Okay. So d value of S is 0, and 0 plus 9, it will be since this less than the existing d value, so it will replace by that. 0 plus 14 less than infinity, so 14 will be this, and 0 plus 15 will be replacing. And if you wanted to keep the parent information, then all of the parent of these nodes would have been set to S in the bookkeeping. Earlier it was unknown. Now, okay. Now this completes the first step, and the situation is like this. And accordingly, the order of the nodes here will change, because this node 2 has the minimum d value right now. It is 9, 14, 15. So node 2 will appear to be the head. So next extract mean will extract 2 and put into S. Okay. And once I do that, now anyone, this particular node now will be visible to me, because this is directly adjacent to 2. Okay. So again, what will be the condition? 24 plus 9 is less than infinity. So the d value of this node 3 will be replaced by 24 plus 9, that is 33. Okay. And accordingly, this 3, now all the nodes which are present in PQ, see, minimum is 6, then 7, then 3, then other nodes. So it will change like this. This 6 will now be added. Okay, 6 will be added, and this process will repeat. So when 6 gets included in S, then now see who are the adjacent of 6? 3, 5 and 7. Now 3 is still not included. So there is a chance that we could update. And here you can easily see what is the distance of 3 going through this path is 14 plus 18, which is 32. And what was the earlier value of the value of 3? 33. So it will be updated by 32, and in the bookkeeping, parent of 3, which were now earlier set to 2, will be changed to 6. Am I clear?
Yes,
This
sir.
change is important, you see.
Yes, sir.
Huh? Similarly, for 5, it is quite easy because it had a d value infinity. So anything will be less than infinity. So it will be replaced by 30 plus 14, 44. Here, here it was 15. Now what is the length of the path via 6? 14 plus 5, which is greater than 15. So we will not update the value of 7 and parent information 7. So inclusion of 6 will modify the value of 3 and the value of 5 only. The value of 7 will remain unchanged. Okay. Now, uh, from the present nodes in priority queue, which one is having the minimum distance? 3 is having 32, 4 is having 44, 5, where is 5? Uh, there is no 5, no? 3, 4, 3. Yes, 5. 3, 4, where is 4? Yeah, 4 is infinity, 5 is 44, and 7 is 15, t is infinity. So obviously, now 7 will be having the will be extracted because it is having the minimum distance. So 7, when we include 7, who are the adjacent of 7? Only t and 5, these two. So now let's see what was the earlier weight of 5? 44. Now through this path, 20 plus 15, 35. So it will be updated, and this will also be updated because it was earlier infinity. Now it will be 44 plus 15, that is 59. Okay. So next, among these 4 nodes within this priority queue, who is having the minimum weight and minimum distance? 3. So 3 will be included, and by including 3, now only new adjacency thing is this t. From 3, t is adjacent. So d value of t will be updated to 51 because it was 59 earlier through this path. Now from through this path it will be 32 plus 19, which is 51. So it will be updated. Now from 4, 5 and t, which one is having minimum? 4, 5, not 5. 5 will be included, and once 5 gets included, the d value of 4 will be changed from infinity to here it was 34 plus 11, 45. Okay. Now among 4 and t, the d value of 4 is less than t. So 4 will be included, and the d value of t will again change from 51 to 50 because 45, no, will it change? It's 6, na? So it will not change actually. If it would have 5, then it would have been changed, na? 45 plus 5 probably. It has to be 5, then only it will change. Okay. So this edge would be 5 instead of 6. This is a wrong thing. Okay, and you see in this figure how this thing actually gets propagated. So this is like a BFS. You can easily see the nodes gets starting from this S, the entire graph gets explode like a BFS. Okay, is it okay?
Yes, sir.
So what was the problem with last step?
Last step, see here when I included this four. Huh?
Yes, sir.
Now what I have shown here that, oh no, the 50 was,
Sir, 5, node 5.
oh, okay, okay. When we included 5, the automatically that change had occurred, na? Okay. No, no problem, no problem. Yes, I have missed this one. When this 5 was getting included, then it was updated to 50. Yes. So there was no change. The last. Yes, yes. Okay. So this is actually this Dastas algorithm is applicable when, in the most real cases, it is applicable when the age weights are non-negative. Okay. So, in fact, when you have non-negative, I mean, negative cycle, then it is not defined, sort of path problem. It's not defined, but typically in almost all real life example, we find that age weights will be non-negative, so it will be applied. And in under what case it may be negative, I had shared with Abhishek one discussion that day. We were having some discussion about what is the significance of negative age weight. Hopefully, you have followed that discussion. It has given some possible examples of cases where graph weights can be negative. Okay, so this concludes our discussion on graphs. There are many other problems. Hopefully, you will be learning them in this particular semester under analysis, design and analysis of algorithms. Okay, but these are the fundamental uh, problems, and I have tried to at least give some idea how to solve them. But it is, you have to implement them. That is the main challenge. Okay, although this philosophy looks like, with illustrative example, it looks like easy, but when you try to implement using programming, it will be tricky. So I'll suggest that you try to implement them of your own. Maybe nowadays you may not need to solve this problem of your own. You will get enough library packages to solve that. But solving these basic problems of your own will enable you to handle pointers to a great extent. Okay, and also there will be many other things which you will be able to practice. So I'll suggest you try to solve this type of problems of your own using C. That will enhance your skill to a great extent. Okay, because you, as a computer science student, you should know how to use pointers. Okay, although in most of the cases nowadays people do not use C, but I think using C, because C is more closer to the low level programming, so you will have some idea. So those who will be actually working on system programming, doing some changes in operating systems, for them this type of handling pointers and solving this type of problems will be beneficial. Okay, so uh, let me move on to this integer sorting part. So basically, we'll be discussing two famous integer sorting. One is counting sort, and another is radix sort. Okay. So basic philosophy of such sorting is, let me elaborate that whatever sorting algorithm you have so far learned, uh, Which one do you think? I think you have learned at least six sorting algorithms in this course. You have at least heard and learned, na? Like insertion sort, bubble sort, then selection sort, and quick merge and heap, isn't it?
Yes, sir.
Yes, sir.
Now, so what is the common thing in all of this sorting? And which one do you feel the best?
Heap
Hmm?
sort.
Hmm?
And
So worst case time complexity wise,
Sir, n log n, which is merge
merge
sort can also do.
so merge, quick, and heap, all of them gives you order of n log n worst case. Hmm?
Yes, sir.
And
quick sort. Quick
hmm?
sort.
Quick sort. Quick sort, why not? See, quick sort, you might be very much dependent on that pivot selection. Huh? Quick sort, there is a confusion that in where you order of n square when array is already sorted. But actually, quick sort definition depends on, it depends on implementation. When you choose the first element as the pivot, then there is a chance that when the array is already sorted, at every step you will get a very skewed partition. That means in the left partition, maybe there is nothing, and right partition n minus 1. But you can change your implementation. There are two strategies. One is that you can always choose the median as your pivot. Okay, instead of always fixing the first element to be pivot, you can update your implementation by selecting median at every step. Now, theoretically, then it can be proved in that case, worst case performance would be also in log n, because you will hopefully you will be able to learn that median finding, that kth smallest element, finding kth smallest element from a given set of elements. That is a famous problem in computer science. I hope that problem will be discussed in this fourth semester course. There you can find it in linear time. Obviously, the constant is very large. Okay, although it is a linear time, that means proportional to n, but in practical sense, it may not be that much. But theoretically, it can be proved that using that kth smallest element, median could be found in linear time. Now, so if you now think of an implementation of quicksort where at every step, instead of choosing the leftmost or first element or rightmost element as pivot, you are always choosing median as your pivot element, and you are applying that linear time algorithm to find the median. Then the worst case behavior of quicksort will also be order of n log n theoretically. But in practice, this n log n, as I've said, the linear time, even if it is linear time, the constant, multiplicative constant is very high. That's why in practical scenarios, it may not perform that much better, but theoretically you can say. And there are another philosophy of quicksort, that is randomized quicksort. You probably will be given some idea about randomized algorithm, where you will find the randomized version of quicksort will also perform in order of n log n time. But anyway, that is beyond the scope of this discussion. What I intended to point it out, that all the sorting algorithms you have so far learned, the basic operations, they have considered that key values are comparable. That's why all of them have uh, used comparison as the fundamental operation. You consider any of these six algorithm. Okay. So, although we have illustrated mostly as if key values are integers, but in real life, key values may not be integer. But all these 6 algorithms will be applicable if some way or the round we can compare the key values. Okay. It need not be integer or any number. Even in non-number, like it can be some alphanumeric character also. We can compare. So any key value which can compare, if you have a list or array of objects which can be compared by some means, which can be compared for greater than, less than, this relation and operations will be applicable, then we can apply these sorting algorithms, all of these 6 sorting algorithms. And it can be theoretically proved that the best possible worst case time for solving such a problem when our keys are comparable using any comparison sort, irrespective of whether it is selection sort or anything, any sort, you can devise your own sort, but your worst case you cannot improve beyond order of n log n. Okay. The theoretically proof of that statement is very tricky. I don't know whether that will be covered in your syllabus, but you can easily assume that. You can always find this thing in computer science, that the best possible worst case for comparison based sort is order of n log n. Are you getting my point? You cannot devise any algorithm, any sorting algorithm which can be applied to objects which can only be compared. That means your algorithms will use comparison as a fundamental operation. Then the worst case, the best possible worst case will always be order of n log n. So if you devise a new algorithm and prove that your algorithm runs in the worst case order of n log n, that means that is an optimal algorithm. No one can do better than that. Understood?
Yes, sir.
Okay. But in real life, we may have some problems where our key values can have some more additional property which we can exploit to speed up the sorting procedure. Like when we have keys which are integer, then we can also perform some other operation. We are not bound to restrict ourselves only in comparison. We can perform some other operation, and we can define our algorithm to be applied in that restricted case, like that will be applied on integers only or some key values with some specific property. Then we can improve this bound. Okay. And this integer sorting is basically deals with that kind of sorting algorithm which will be applied, mostly applied to integer key values. And we'll see that in that case, the worst case can be improved to order of n. But very, very seriously, you try to distinguish these two classes of algorithm. One algorithm, which we call comparison sort algorithm, those can be applied to any kind of objects whose key values can be compared. Okay, so those are applied to integer objects also, no problem. But this integer sorting, which will perform order of n in linear time, their application is restricted only within some special kind of objects like integers. Okay, so if you are asked that what is the best possible worst case for sorting, you should not say order of n always. It depends on what type of, in general, is it comparison sort or it is integer sort. You have to know that what is the application domain. Okay, so that you should keep in mind. So integer sorting basically will so apart from comparison, many more operations can be done in constant time. So we'll be able to use that to get better running time. And counting sort is one type of fundamental integer sort. It sometimes a variant of counting sort is known as bucket sort also. Okay. So the idea is something like that. Suppose we have been given an array to be sorted, okay, and the all the key values to be sorted are integers, and we know that the range of values that appear in this array, that means there are n number of elements and they assume different values, but there is a fixed range of values, that is the minimum value and maximum value we know. Okay, suppose the maximum or highest or largest value is say k. Okay, this represents k. Here in this particular example, n is 7. There are 7 elements, and largest element value that can be possible is 9. Okay, although 9 is not present here, but suppose from the problem domain we have understood that the values will be varying from 0 to 9. Okay, so in that case, how we can solve this problem? Let me illustrate, you will understand. So n is the number of elements to be sorted, k is the value of the maximum key, assuming key values are within range 0 to k minus 1. Okay, k is the maximum value, which here I have assumed that k will not be there in the thing. K minus 1 is the maximum. Okay. Now, what is the philosophy? Philosophy is that we will keep an array count whose size will be exactly k. Okay. So each position of this count array is representing the possible range, like 0 to, suppose if my range is something like 5 to 15, then this 0th index would have been representing 5 and this may be 14. Okay, so in that way, so the size of the count will vary with the range. Now without loss of generality, we can assume that the left edge of our range starts from 0. If practically it doesn't start from 0, we can just make an offset to make it 0, like this. So each of these cells in this counting array represents the values within this range. Okay, and as the name suggests, here it is used to store the number of elements for a with a particular value. We will scan this given array to get that how many threes are there. I will put that number here. How many fives are there? I will put that number here, in this way. So the possible range, the possible values starts from 0, ends at 9. Okay. So I start with this array, then actual algorithm starts. I scan this given array from left to right. Since I have got a 1 here, so I will go to the 1 index of this count array. Whatever may be the value, that value I will go to that index of the count array and increment the value by 1. Okay, whenever I found a 1, that cell value will be incremented by 1. Similarly, next 3. So I will go to count 3 and I will increment the value. 4, I will go to 4, I will increment the value. 7, I will increment the value here. Again 4, so I will increment the value. So I will get a 2 here. 6, I will increment this value. 1, I will increment this value. So after one scan of this original array, what I found, I have calculated the number of occurrences of each of these values. Are you getting my point? Hello?
Yes, sir.
Okay. So this is the strategy. Now, next phase of the algorithm, I have to traverse this count array. Okay. And what I will do, if there is a non-zero value, I will stop there and replicate them. If there is more than one, if there is one, I will just write the value, the index value once. If there is 2, I will write the value 2 twice. Okay, so here this is the starting point of the array. So I am scanning here 0, so nothing. Here 2, 2 means I have 2 ones, so I will write 2 ones here. Okay, then this is 0, I'll skip. Here 1, so I will write 3 next. Okay, similarly under 4 I have got 2, so I'll write 2 fours. Okay, similarly this will be skipped. Then 6, I'll write 6, then I'll write 1 7. In this way I will explore the entire array and automatically I get the output.
Sir, excuse me, sir.
Yes,
Sir, actually, we have a class now.
you have a class.
Yes, sir.
So why at the start you have not told me? This is becoming very difficult. Who is that? Sornabo?
Yes, sir.
Okay, then what will happen? Then suggest me. Should I complete this counting sort at least? It will take
No, no,
5
Sir,
sir,
minutes.
sir.
actually, just now
Sir,
class
you
is
can
going
keep
to
taking the
start
class.
on math.
Huh?
Sir, you can keep taking the class, sir. We will join that one a bit late, sir. It's fine.
Sir, actually, that class is
No, no,
supposed to
no. This
start
is,
from
if that is a
5:30.
regular class, you should
No,
join.
sir, it's not a regular class, sir. It's a surprise class. I mean,
Extra class, sir.
it was just told, sir.
Okay, let me complete the counting sort. The Reddick
Yes,
sort
sir.
part,
No,
maybe
sir, you
I'll
can
be.
complete the class, sir.
No, no, I don't want to get into any controversy. I will send you the material. Then, if you don't understand, you give me another class. I will let you. Let me complete the counting sort only. Okay. Anyway, so now let's see this while performing the second scan. That means scanning the counting and getting the output. We could have used the same array, isn't it? Because once we have made the first part and constructed this count array, then the content of this original array may be irrelevant. Because see, we have already taken into account that how many threes are there, how many twos are there, how many. So just by referring, so we, instead of using a separate array, we can override this original array in order to save space. Can we? Are you getting my point? What I am saying? Instead of starting with a new fresh array, I could have override this A array to get the final output when I am performing the traversal in the count part.
Yes, sir.
Okay.
Sir, but if
But
we will override the array, we may change some elements we have not encountered yet.
no, why?
If
I
we
have
override the
see.
original array, actually, without using that count array.
Yes, fast. I have performed the entire scanning of this original array and I have constructed this the entire count array. Then I am the third pass when I am actually scanning this count array to get the output. What I am saying, instead of using a separate array, I could have output that because I don't need these values anymore.
Okay, sir. Okay, sir.
But there is a catch, obviously. There is a catch. Here, what we are assuming that as if the objects are only key values. In practice, as we have already said, that these key values are only some special values for any object. There are some other information associated with that. That is called satellite information. That may be the main data. So I cannot just use this thing in that case. Okay, in practice, if I am given only the key elements, there is no satellite information associated with the key element. That will be very rare. In that case, I can only overwrite. Okay, but in practice, since these key values are only special values, along with them, there are many satellite information. So these three, these four and these four are different. This 4 is key value, but the actual object under this 4 may be different from this 4. isn't it? The satellite informations may vary. So overwriting these two may be costly. Okay. I mean, not only costly, it is not allowed, maybe. Okay. But one point you could notice that this algorithm is stable. When we have same key values, the, the object which appears in the original array first, that will appear here first. If we don't overwrite it, when we are using dedicated output array, then this implementation, a straightforward implementation is stable. Do you know stable sort? I think ma'am had discussed stable sorting.
Yes, sir.
So counting sort inherently a stable algorithm, and that is a very a strong point which you will see will be useful in Reddick sort. Okay.
How it is stable?
So let's begin.
Hmm?
Sir, how it is
Now,
stable? Like
I'll just
if 2, 4 are there in the array, then we are just keeping the count.
No, when using this, I am not using this array as the output array. That time I can implement na 2 to 1 is 2. So I will just pull out this object one by one.
Yes, sir.
the
Okay.
formal
So I'll see, actually we will be using an array of linked list to implement this counting sort. Then this stable property will be more evident. Okay.
Sir, excuse me, sir.
Yes.
Sir, actually our class has already started.
Okay. So you may leave. You may leave. Uh, so what could be done next? So you may leave, Sarnav. And any other else who want, all of you will leave, or I should complete this counting sort? Tell me. Hello?
Sir, you can complete, sir.
Okay, let me complete this counting sort at least, as I have said. So it's very annoying. I mean, so as I was discussing this implementation issues, reusing the original array as the output array would not be straightforward for elements containing other data items, which are called the satellite information. So may require several shifts, thereby may degrade the actual performance. Okay. So what we do actually, the count, instead of using an array, we use a array of linked list in case of constructing this count. Okay. Then it will be very straightforward. So this is our array, given array, and see this, apart from these key values, I have shown some strange characters that are actually indicating the satellite informations. Okay. This is just for illustration. Same thing. So count will be an array of linked list. Now, when we'll actually scan this original array, we'll pull out the element. We pull out the objects and attach in the appropriate place in this array as array of linked list. Okay. So when I am getting a 1, so I will come to the index 1 and I will pull the entire object and attached at the head of the linked list. Then when I encounter the next one, I will attach at the end of this linked list. That is the policy. So I am keeping the entire object in the count array. Okay. So similarly 3 will come here, then 4 will go there, 7 will go there, then 4 will again be encountered, but this is a different object. Although key value of this resembles with the earlier one, but this is in another object, so I will just attach it the end of this linked list. Okay. So 6 will be going there and 1 will be attached at the end. So now this count array of linked list contains everything. Now I can easily override this array. Understood my point? Now I don't need this one. I'll just traverse this array of linked list in a sequence and I will get the sorted array. I'll pull up them and place them in this array, override them, no problem. No information will be lost. And stability is also apparent because see this array of linked list I am attaching at the end. So whoever appears in the original array first is coming in the corresponding linked list ahead of the other. Okay, so I will be getting like this, just sequentially performing this one will be overwritten, then this one, this three, this overwrite will not do any wrong thing. Okay. Is it clear?
Directly
Yes, sir.
to the
Okay. Now, so stable sorting is already evident because the whoever comes here, this one, red one comes before green one, here also red one comes before green one. Similarly, red 4, green 4. It is quite apparent from that, it will be stable. Now, why we are so much bothered about stable sorting? Because the radix sort, okay, this complexity I had forgot to mention. Here I had mentioned the time complexity. Order of n plus k, because I have to traverse n time first. N is the number of elements, and then when getting the output I have to traverse k times, because this is the size of the count array. So it will be order of n plus k, and it will be proportional to n, provided that k is almost same to the number of elements. So this order of n appears, this order of n or linear time is achievable only under very restrictive constraint. Okay, when the range of values is almost similar to the number of elements and all the key values are of integer, then only we can achieve this order of n. But still, it will be able to see that in many real life scenarios, we deal with integer keys only, and that key, the possible values of keys are also restricted within a range. So this type of sort is important. Without looking at that, if we used complex algorithm like quick sort, merge sort, or heap sort, it will be just wastage of or underutilization of the system. Okay. Now this radix sort is basically another integer sorting, which will use counting sort or any other sort which is stable. You can easily see. Okay, so I'll circulate these slides which I have made, add much illustration as possible. Hope you will be able to understand everything. Okay, so I am stopping here, but still if someone of you find it difficult, then he or she may personally contact me to clarify the issues. Okay, so uh, shall I conclude the session? Hello.
Yes, sir.
Okay. Okay, then hopefully next week sometime, if we really find and before giving me the time, you should explore. Okay, it is very demoralizing for me that I had to start late, I had to end early. This type of thing is very
So actually, I had informed day before yesterday itself in like the main group. So the other CRs of Y and Z, in case if you have any classes overlapping with the time that I ask you or like request, please do let me know, because I don't know your schedules exactly. If you have some extra class or something, so if you see the classes in the overlapping time,